Definition of facies. In geology, the term facies refers to a distinct assemblage of sedimentary rock characteristics that reflect the environmental conditions present during its formation. Facies are defined by a combination of sedimentary structures, lithology, rock type, fossil content, and other physical and chemical properties. Each facies represents a snapshot of the depositional environment at a particular time and place within the Earth's history. Facies analysis is a fundamental aspect of sedimentary geology, as it allows geologists to reconstruct past environments and understand the processes that shaped the Earth's surface over time. By identifying and interpreting different facies within a sedimentary sequence, geologists can reconstruct ancient landscapes, such as river channels, shorelines, or deep-sea environments, and infer the processes that operated within these environments, such as erosion, transport, and deposition. Facies can vary widely depending on factors such as sediment source, transport mechanisms, energy levels, and depositional setting. For example, a coastal environment may exhibit facies characterized by sandy beaches, mudflats, or tidal channels, each reflecting the specific conditions of wave action, tidal influence, and sediment supply. Similarly, a deep-sea environment may contain facies indicative of turbidity currents, pelagic sedimentation, or deep-water currents, reflecting the unique conditions found in the abyssal realm. The study of facies is essential not only for understanding past Earth processes but also for predicting the distribution and characteristics of sedimentary reservoirs, such as oil and gas fields. By correlating facies across different regions and basins, geologists can identify potential areas of hydrocarbon accumulation and optimize exploration and production strategies. In summary, facies represent the sedimentary record of past environments and are key to deciphering Earth's history, understanding sedimentary processes, and locating valuable natural resources. Facies types. In geology, facies types refer to the various categories or classifications of sedimentary rock characteristics that are used to describe and interpret different depositional environments. Facies types are defined by a combination of sedimentary structures, lithology, rock type, fossil content, and other physical and chemical properties. They provide insight into the conditions under which sediments were deposited and help geologists reconstruct past environments. There are numerous facies types, each associated with specific depositional settings and processes. Some common facies types include fluvial facies. Fluvial facies form in river environments and are characterized by features such as cross-bedding, channel fills, and riverbank deposits. Sediments in fluvial facies typically include sandstones, siltstones, and conglomerates, reflecting the high energy of river systems. Marine facies. Marine facies form in various marine environments, including shallow marine, shelf, and deep-sea settings. Shallow marine facies often consist of carbonate rocks such as limestone and dolomite, along with sandy deposits and reef structures. Shelf facies can include sandstones, shales, and limestones deposited in relatively shallow water depths. Deep-sea facies are characterized by fine-grained sediments such as mudstones and siltstones, often deposited by turbidity currents or pelagic settling. Deltaic facies. Deltaic facies form at the mouths of rivers where sediment is deposited as the river enters a standing body of water, such as a lake or sea. These facies typically include coarser-grained sediments near the delta front, such as sandstones and conglomerates, grading into finer-grained deposits like siltstones and mudstones further away from the delta. Lacustrine facies. Lacustrine facies are associated with lake environments and can include a variety of sediment types depending on factors such as water depth, energy levels, and climate. Common lacustrine facies include laminated mudstones, evaporites, such as gypsum and halite, and organic-rich shales. Glacial facies. Glacial facies form in environments influenced by glaciers and ice sheets. These facies typically consist of poorly sorted sediments, including till, unsorted glacial debris, glacial erratics, large boulders transported by ice, and glacial outwash deposits, sand and gravel sorted by meltwater streams. Aeolian facies. Aeolian facies are associated with wind-driven processes and occur in environments such as deserts and coastal dunes. Aeolian facies often include well-sorted sandstones with crossbedding, dune structures, and wind ripple marks. These are just a few examples of the diverse range of facies types found in sedimentary environments. By recognizing and interpreting facies types, geologists can reconstruct past landscapes, infer depositional processes, and better understand Earth's geological history. Facies formation. Facies formation is a complex process influenced by a variety of factors including sediment source, transport mechanisms, depositional environment, and tectonic activity. Understanding the formation of facies involves examining the interplay of these factors over time and how they contribute to the development of distinct sedimentary rock characteristics. Sediment source. The source of sediment plays a crucial role in facies formation. Sediment can be derived from various sources such as weathering and erosion of bedrock, transportation by rivers, glaciers, wind, or even volcanic activity. The composition and texture of the sediment supply influence the lithology and grain size of the resulting facies. Transport mechanisms. The way sediment is transported from its source to its final deposition site impacts facies formation. Different transport mechanisms, such as fluvial, river, aeolian, wind, glacial, ice, or marine currents, result in distinctive sedimentary structures and sorting patterns within the facies. For example, well-rounded grains in a beach facies may indicate long periods of transport by waves and currents, while angular grains in a glacial moraine facies suggest minimal transport. Depositional environment. The depositional environment refers to the specific geographic location and conditions where sediment accumulates. Factors such as water depth, energy levels, temperature, salinity, and substrate composition influence facies formation. For instance, a high-energy marine environment with strong currents may favor the deposition of coarse-grained sands and conglomerates, whereas a low-energy lagoon environment may promote the accumulation of fine-grained muds and organic-rich shales. Tectonic activity. Tectonic forces, such as plate movements, can exert significant influence on facies formation by altering depositional environments and sedimentary processes. Tectonic activity can create subsidence or uplift, leading to changes in sea level, basin geometry, and sediment supply. For example, the formation of mountain ranges through tectonic collision can produce coarse-grained sediments in nearby basins through erosion and deposition processes. Diagenesis. After deposition, sediment undergoes diagenesis, which refers to the physical, chemical, and biological changes that occur as sediment becomes rock. Diagenetic processes such as compaction, cementation, mineral alteration, and fossilization can modify the original sedimentary fabric and contribute to the development of unique facies characteristics over time. Overall, facies formation is a dynamic process influenced by a multitude of factors acting over various spatial and temporal scales. By studying the sedimentary record and interpreting facies characteristics, geologists can reconstruct past environments, decipher Earth's history, and gain insights into the processes shaping the Earth's surface. Facies analysis. Facies analysis is a comprehensive approach used by geologists to interpret sedimentary rocks and reconstruct past environments based on the characteristics of sedimentary facies. It involves the systematic study of sedimentary facies within a rock sequence to infer the depositional processes, environmental conditions, and geological history of a particular area. The process of facies analysis typically involves several key steps. Field observation. Geologists start by conducting fieldwork to observe and document sedimentary rock outcrops. They record observations such as lithology, sedimentary structures, bedding patterns, fossil content, and any other relevant features that help identify different facies within the rock sequence. Stratigraphic analysis. Geologists establish the stratigraphic context of the sedimentary sequence by examining the vertical and lateral relationships between different rock units. They identify boundaries between sedimentary layers and correlate them across different outcrops or wells to reconstruct the spatial distribution of facies within a geological basin. Facies description: geologists describe the characteristics of each identified facies in detail, including grain size, sedimentary structures, such as cross-bedding, ripple marks, or mud cracks, fossil assemblages, mineralogy, and any other diagnostic features. This information provides insights into the depositional environment and processes that formed each facies. Facies interpretation: based on the observed characteristics of the facies, geologists interpret the depositional environment in which each facies formed. They consider factors such as water depth, energy levels, sediment source, climate, tectonic setting, and sea level fluctuations to reconstruct the paleo-environmental conditions prevailing during deposition. Sequence stratigraphy: geologists apply principles of sequence stratigraphy to analyze the hierarchical arrangement of sedimentary sequences and identify depositional cycles, bounding surfaces, and depositional systems tracts. This helps in understanding the evolution of sedimentary environments over time and correlating facies across different stratigraphic intervals. Paleogeographic reconstruction: by integrating facies analysis with regional geological data, geologists reconstruct paleogeographic maps depicting the distribution of different depositional environments during specific geological time periods. These reconstructions provide valuable insights into the evolution of sedimentary basins and the interactions between tectonics, sea level changes, and sedimentation. Facies analysis is fundamental to various applications in geology, including hydrocarbon exploration, reservoir characterization, paleo-environmental reconstruction, and stratigraphic correlation. By unraveling the complex history recorded in sedimentary rocks, facies analysis contributes to our understanding of Earth's geological evolution and helps inform decisions in resource exploration and environmental management.